Okay, so now we are going to look at this chapter, and we're going to jump right to here. And we're not going to follow the full approach that they use in this text. We're just going to review some of the ideas that hopefully you're already familiar with. So they give the definition of derivative. This is just the standard function from R to R, so it's just a very simple function with just one input and one output. And then they go through a kind of slightly different way of defining partial derivatives, but I'm not going to go through any of that. I'm just going to assume that you have seen it before, but I will just review what it looks like. So here we have a function of two variables, unlike the previous situation. And so in effect, we have three variables because we have the output variable as, for example, z, and then we have these input variables. So this is a picture of maybe what this function looks like, maybe. If I try and plot this in Google, it doesn't really look anything like that. Maybe I didn't type it properly, but anyway, we won't worry about that. We'll just assume that it looks like this. And then the question is, what is the partial derivative? And we can, as you probably know, we just treat y as a constant because we're asking for the partial derivative with respect to x. So we get this result, and if we do the partial derivative, okay, and another example, if you have g as this function, you can calculate this is just a different notation for the partial derivative of g with respect to x, the partial derivative of g with respect to y. Okay, and then this notation just means that after you calculate the derivative, you put in the values for x and y. Okay, so now here's a function that has many input variables and just one output variable. So an example might be, just like we've been looking at, so here we have n different variables here. They happen to be all squared. So we have a function of these n variables, and then we have an output variable, which they're just denoting by x sub n plus 1. We might call it like y, or we might have called it z, but here they're just calling it x sub n plus 1. But just so you don't get confused, it's like z equals x1 squared plus x2 squared, and so on. So we have n different input variables. So we could ask for the partial derivative of z with respect to x1, the partial derivative of z with respect to x2, and we could just keep going until we got to the partial derivative with respect to xn. So that's exactly what we were just talking about a few minutes ago. So to keep things just a little bit more organized, we can write that as, let's say that function was called f. So going back to here, the function here, which is the output variable is z, but we can call the function like that if we want. So instead of saying the partial with respect to partial of z, z with respect to x1, z with respect to x2, we can say the partial of f with respect to x1, the partial of f with respect to x2, and so on. And we're just going to put them in like, kind of an organized way here. So we put the first one and the second one and put brackets around them like this. And actually this forms a vector. And, it has n pieces. So it's a vector in kind of n dimensions. But this vector is not, the elements of this vector are not numbers per se. So I wouldn't want to say it's a vector in Rn because that would mean that we're talking about n elements, but each element should be a real number in order to say, and that's what we usually talk about. So each number is like, each element is like a number, so we might have like 3 and 2 and 9 and so on. That would be a vector in Rn if there were n pieces here. But when we say Rn, it means this R stands for real numbers. So it means that each of these entries should be a real number. But that's not the case here. Actually, we saw that each of these is like a function. Let's just go back and check that. So here, the partial of f with respect to the first input variable, that would be like x1 in the notation we were just looking at. But here we're calling it x and y. So instead of x1 and x2, we're calling it x and y. But anyway, the partial of f with respect to the first variable, it's not a number. This is not a number. This is a function. So I don't want to say that the result, when we put these together, like put this one in here, and this one in here, I can't really say that's in Rn, because if these are not numbers in here, this is not a number, this is not a number. So, but it is still, this is a two-dimensional object. I can say that. I just don't want to say it's in I don't want to say it's in R2, because R2, as I just said, implies that these are numbers in here. They're not. They're functions. So we just don't want to say that. Okay, so going back to this, we have the partial of f with respect to x1 and x2 and x so on up to xn. And so this is just like an organized way of writing all the partial derivatives for like this function. We have partial derivative with respect to x1 and the partial derivative of this whole thing with respect to x2 and so on. So we have all of those partial derivatives that we can think about, and we just want to put them in like an organized list. So we do this, we put them in this organized list, but then we can recognize, oh, that list, we can think of it as a vector itself, which is maybe a nice thing to think about. But anyway, this is just a list of all the partial derivatives, and we give it a name, and it's this. Now, just one more thing. Why is this x bold? Because that's to tell us that the input into f is not just one element, but there are many. It's got x1, x2, x2. So x, that bold x, is so it's got x1, x2. So that's why, right? We have many inputs into our function, and so we can express that as saying it's a function of many inputs. A nice quick way to write that is that it's a function of the vector x, and this is the vector x. So this is just a nice handy list, and we call this list this thing, and we read this thing as the gradient of f. So the gradient of f is just all the partial derivatives put into a handy list, which actually is a vector. So we just want to have this definition. And just like we might ask if we have the partial of f with respect to x, and then we say, what is that at a particular xy pair? We put in the 0, for example, and the 0, and we get out some result when we evaluate it at a specific point. So in the same way, with this gradient, we can say, well, what is it when we put in a particular value of x, and when we say a particular value of x1, x2, x3, x4, we're saying a particular value for the vector x. So we're filling in all of these things, and we get a particular one. For example, we might say when x1 is a1, sorry about that, when x2 is a2, where a1, a2 are particular numbers, and a and so on, up to the end. So, and then we'll call that a. because, this might naturally be called A. So we want to know what's this evaluate to when we put in um, a particular set of values A, and then of course we put in the particular set of values into each of these pieces. So that this is the gradient, and this is which is a vector, and this is the gradient evaluated at a particular point in the n space. Okay, let's just try and take a quick look at an example here, just to give us some, make this a little bit less abstract. So suppose that we have a function, as you can see here. Now, unfortunately, she gives us kind of weird notation, so let me just change it. So she uses this variable here, but let me just call it z. So here we have z as a function of x1 and x2 and xn. And it's a pretty straightforward function. It's just the square of x1 plus the square of x2, and so on. So if we want to make it even more concrete, we could just say something like this. So we could just say that. So here, x1 is x, and x2, I'm calling it y. So that's a little bit simpler. And we only have two input variables. And then we have the one output variable. So here we're just allowing for more, but let me just do this one because it'll mean I'll have to write less. But here she says this is in R n plus 1, but there are only n variables here. So what is she talking about? Why n plus 1? So analogously here, she would say that this is in R3. And why is that? There's only two input variables, but because there's a third variable here, so the whole thing, in order to graph it, we need R3 here, right? So in order to graph this one, we need Rn plus 1 because it's n inputs, then we need one output. So the total to graph it, or to sort of think about it, it exists sort of in Rn plus 1, just like this kind of exists in R3. Now, we know what the partial of this is with respect to, we know what each of these is partial of z with respect to x, partial of z with respect to y. This is just 2x, and this is just 2y. So in general, it's going to be the partial of f with respect to x1, x2, they're all going to be like the same, just like these are sort of all the same. Just going to be 2xi for all of these, so for all the i's, or for all the different possible i's. Okay, so what is the gradient in this sort of smaller example? It's just the partial of each. It's just this, but here we're only going to have two. So what's it going to be here? So the gradient of f in this cleaner, smaller example is just 2x, 2y. And here it's going to be, we're going to have to write it all out. So it's going to be 2x1, 2x2, all the way up to 2xn. And now we can ask, what is it at a particular point, a particular a? So by a particular a, we mean in the input space. So, x can be 0 and y could be 0, or anything. X can be anything and y can be anything. So let's just make something up. So, for example, when a is 1, 2. So that just means we put in x equals 1 and y equals 2 into the gradient, into here. So what do we get? We get 2 and we get 4. So we get 2, 4. So that's the gradient at this a, and that's written like that. So what is it? It's 2, 4. Oops, sorry about that. Okay. And what does that tell us? That tells us that when the input, remember this is the input, let's call this x, and this y, and then we have another dimension, z. So, this is saying when x is 1, 2, so we go 1 here, and y is 2. We're like this place in the xy plane, then the height is somewhere out here, whatever it is. What is the height? the function is this, so it's 1 for x and 2 for y, so that's 1 squared plus 2 squared is 1 plus 4, which is 5. So the height is out here. So above this point, it's kind of hard to draw it, but above this point, the height is 5. Anyway, what we're saying is at this point, 1 comma 2, 1 comma 2, the gradient, which is kind of the partial derivatives in the, it isn't kind of, it's the partial derivatives in the x and y directions. So, you know, we have some kind of surface up here, like maybe it's an umbrella, and if we fix x and we only change y, then that derivative I think was 4. And if we fix y and only change x, then that derivative is 2. So, so it's telling us like what the derivative is in each direction, in the x and y direction. But we say at this point. So it's a little confusing because we are saying at this point in the xy plane what the derivative is, what the gradient is, but it's the, you know, it has to do with the slope of this picture out here. It's a little bit confusing, but anyway, we're talking about the input is only in 2 dimensions, even though we said that the function was in R3, right? But the input is only 2 dimensions, and so we talk about the gradient at this point. So that's a little bit confusing, but hopefully it doesn't confuse you. Okay, and then they have another definition to make things a little more complicated. You know, this is really enough actually, but we can also have the same thing here that we have here. We just have here, we have round brackets around it, and here we have square brackets, and we don't have we have commas here, but we don't have commas here. So except for that, it's the same thing on the right-hand side here and here. Now, when we have commas, that means we're talking about a vector, or at least in her book, and when we have just spaces, that means we're talking about a matrix. So, you know, who cares, right? It doesn't matter, you know, whether we think whether we call it this a vector or a matrix. But in some minor sense, it's important, just a kind of bookkeeping sense. But anyway, so um, this is the same stuff as written here. It's just that here we have commas and here we don't. And here we have open bracket or round brackets and here we have square brackets. So except for that, it's the same stuff. And when we write it like this, she means to say that it's a vector. And when she writes it like this, she means to say this is a matrix. So that's the only difference here. And then the name, though, in this case, when we think of it as a vector, is called the gradient. And when we think of it here, it's called the derivative. So what are we going to do about that? We'll just accept her notation. And maybe this notation is somewhat standard, so it might be worth noting it. So let's figure out the gradient for this example. So what we really need to do is take the partial derivative of this thing with respect to x1, with respect to x2, and so on with respect to x3, and all the way up to xn. Well, that's pretty easy, because when you take the partial derivative of this whole thing with respect to x1, all this stuff is just treated like a constant, and so that's just 0, and you just get 2x1. And if you take the partial derivative of this thing, call it f or call it z, whatever you want, if you take the partial derivative of that with respect to x2, then this is 0, and all this stuff is 0, and then we just get 2x sub 2. And you can see the pattern here. You get 2x sub 1, you get 2x sub 2, get 2x sub 3, and so on up to 2x sub n. And so they write 2x sub I for the partial of f with respect to x sub I. So now we have this, we have this, we have all of them. So we can just dump them in here, and that's going to be our gradient. So let's do that. So it's 2x1 comma 2x2 all the way up to 2xn. And that is called the gradient of this function. We can call this function f, or I guess we can call it z, and that is the gradient of, let's say, f. So here it is. And so it's a vector of all the partial derivatives. Okay, and this is the notation for it. So this is called the gradient of f, and this symbol is called nabla. Nabla. So we could say, well, what's the gradient of f at a particular point in this n space, right? We're talking about n space, and so we can say, oh, well, what about when, n space, we have x sub 1, x sub 2, x sub n. So we could say like when x is 2, and I'm sorry, x1 is 2, and I'm sorry, and x2 is 7, that's supposed to be 7, and x3 is 8, and all the way up to xn is like 4, something like that. So we could say, well, what is the gradient at this point? Because the gradient looks like this. We can ask, what is it when we put in this into x1 and 7 into x2 and 8 into the next one, and what did I say, 4 into the last one? We can say, well, what is that? So we can say, let's evaluate the gradient at this particular point. And here in this example, they evaluate this gradient at this point. Okay, so you just put in these values into here and you get something out. Well, I guess this is what you get out. You get 2 times 1 is 1. I'm sorry, 2 times 1 is 2. And this one is 2 times 2 is 4. And the last one is 2 times n. So you get something like this out. And then if you want, you can say what's the derivative of f at this so-called point. And then you put this point or this point into here. I'm sorry, the into the same thing basically, but you don't have the commas and you put square brackets around it. And that's called the derivative, and that's just the matrix form, and this is just the vector form, which is hardly different at all. Like I said, the only difference is here you have commas, and here you don't, and here you have round brackets, and here you have squares, so it's really not any different, or it's only slightly different.